spherical coordinates. Switching to spherical coordinates. Say we started with triple integral over region E of x, y, z, dv. So we want to switch to spherical coordinates. We know how to switch to the polar or cylindrical coordinates. So that is going to be triple integral. Essentially over the same region E, but now we switch everything into the polar or cylindrical coordinates. So I'm going to call it V. F of x and polar are cosine theta, y is going to be r sine theta, and z is z. And have to pay extra price for the switch to cylinder r, and we're going to have dz, dr, d theta. If we want to switch to spherical coordinates, then recall that for spherical coordinates, we need to have spherical coordinates. We need to have rho. In spherical coordinates, we're going to have rho phi theta. That is the same as in cylindrical coordinates. Rho is the distance from the origin toward the point. That's rho. And phi is the angle between positive z-axis and direction toward the point. And if we do projection of a point on xy plane, then projection, distance from projection point of a point toward the origin, that is r. So the connection between r and rho is that r equals to rho multiplied by sine phi. So that's we're going to substitute instead of r here. And if you look, we still need to take care of dz and drs from z and r. So from z and r, we need to switch to rho and phi. Now, if you look to the picture on the picture which we have right there, that is z, that is our angle phi, that is rho, that's our point, and down here we have r. R. That is very similar to the way we switch to from rectangular x and y to polar. We recall that for polar we have distance, we call it r, angle theta, and the price to pay to switch to polar from rectangle is multiplied by extra r. The situation is similar right here. If you look at the picture what we got, so price to pay to switch from z and r to rho and phi, the price to pay is to multiply by extra rho. So we collect that information with what we have before. We have essentially a way to switch from triple integral in regular x, y, z coordinates over region E to triple integral in spherical coordinates. So I'm going to call it over U, which is U is essentially the E, but written in the spherical coordinates. Now we'll have to have our function. We have to have x, y, and z, but we'll need to switch to spherical. So instead of x, we're going to write down rho sine phi cosine theta. Instead of y, we're going to write down rho sine phi sine theta. And instead of z, we're going to write down rho cosine phi. And we need to multiply it by extra r, and xr is rho sine phi, which comes from here. And we also need to multiply by extra r, and by extra r by extra row. So we need to multiply by extra row squared sine phi. That is extra multiple which you need to multiply by, and our variables are going to be the rho d phi d theta. So that is how we're going to be switching from rectangular coordinates, from Cartesian coordinates to spherical in triple integrals. So to switch, we'll have to pay that extra price, rho squared sine phi. So we have a sphere. We want to stay above xy plane. And also we have column. C squared equals to 3x squared plus y squared. Okay. So that's solid E. Solid E is bounded by sphere above xy plane, inside of a cone, and below that sphere. Okay, so inside, side, below. So we don't want to consider a part when z is less than 0. So above xy plane, with restriction, but we have z greater or equal than 0. We don't want to calculate what is happening when z is negative. Okay, so we want to find the volume. Okay, so let's have a look at a picture. So I'll try to do cross section firstly. So that's cross section of a sphere. And then we have a cone, which looks like this. So we will be concerned about that piece. Okay, that's if I do cross section. So if I try to do a three-dimensional picture, my three-dimensional picture might look something like that. So we have a cone. And the cone has a top which comes from that sphere. Comes from that sphere. Right? And it looks like this. Okay. It looks like a cone filled with ice cream, something like that. You see that. Okay. Right, so we want to find its volume. Okay. So we try to switch to spherical. So we'll try to switch to spherical. So we're trying to switch to spherical. So if you're trying to switch to spherical, let's rewrite all the equations in terms of spherical. X squared plus y squared plus z squared, its distance toward the point squared. So x squared plus y squared plus z squared is rho squared. Rho squared equals to 4 is equivalent to saying x squared plus y squared plus z squared equals to 4. Now let's work with the over equation, which says z squared equals to 3 times x squared plus y squared. Recall that x squared plus y squared is r squared. Okay. Then we recall that what z equals to. Z equals to rho cosine phi. So let's move on to the next page and remind you what are our spherical identities. So those identities, how to find rho, right? That's the one that you used. Second identity will be telling you how R is rho sine phi, and z is rho cosine phi. Okay? Because you recall the picture in cylindrical looks like this. So we have z-axis, so z somewhere here. Then we have angle phi. And if we do projection on xy plane, then we have r is right here. So that's why z is adjacent and rho is opposite, okay, from angle theta. And you solve your right triangle and you got what this identity is, z equals to rho cosine phi and r equals to rho sine phi. So we have z squared equals to 3r squared. So z equals to rho squared cosine squared phi equals to 3 rho squared sine squared phi. Then the rho squared will be cancelled out. And we're going to get sine squared over cosine squared equals to 1/3. Sine phi over cosine phi equals to 1/3. Not sure why I switched to yellow one. Squared. So we're going to get tangent theta squared equals to 1/3. So tangent theta equals to 1 plus or minus 1/3. Now recall that we are working in above xy plane. So we're working about xy plane. So we know that our angle cannot be bigger than pi over 2. So that implies z greater or equal than 0, implies that our angle phi between z-axis and direction toward the point cannot be bigger than pi over 2, because we cannot cross below xy plane. So now if you look at the tangent equals to plus or minus 1/3, so we're going to choose angle equals to pi over 6. So we don't want to consider what is happening when tangent equals to negative 1/3, because if tangent equals to negative 1/3, we're below xy plane. Okay. So tangent equals to 1/3, and that is pi over 6. And it's not 1/3, it's square root of 1 over square root. Okay. So angle equals to pi over 6. So equation of a cone is going to be theta equals to pi over 6. So equation of a cone is going to be theta phi, not theta phi equals to pi over 6. Equation on top is going to be rho squared equals to 4, so rho equals to 2. And we are ready to set up our integral. Okay, so let's set up our integral. So again, equation on top here is rho equals to 2. Equation of this guy is going to be phi equals to pi over 6. So that means rho is going to be changing from 0 till it reaches pi over 2. So from 0 till it reaches 2. So rho is between 0 and 2. Phi will be, we measure the angle from z-axis, and it will be between 0 and at most it's pi over 6. So phi will be between 0 and pi over 6. And theta, because we're going to do, we can do the whole rotation, so theta is going to be between 0 and 2 pi. So what's how going to be our limits? So we're ready to switch to spherical coordinates as soon as we found those limits. So in spherical, So in spherical, our integral is going to look something like that. So integral theta equals to 0, theta equals to 2 pi theta. Integral phi equals to 0, phi equals to pi over 6 d phi. Rho is changing from 0, rho is 2. And inside, don't forget to price to pay to switch to spherical, rho squared sine phi. Okay, so that's how integral is going to look in this case. We have triple integral over t 9 minus x squared minus y squared dv, where t is upper hemisphere, x squared plus y squared plus z squared equals to 9. And upper, we assume that z is greater or equal to 0. So we're going to be switching to spherical. So we're switching to spherical. Can you, I'm going to give you, I guess, a minute or two to figure out if you can figure out what will be the limits for theta, phi, and rho. Okay, can you do that? If we're talking about upper part of sphere, what will be the limits for theta, phi, and rho? What are the limits for rho? You see from here, it implies rho squared equals to 9. So rho is changing from 0 to 3. Because we have restriction, but we are working in the upper hemisphere, we cannot go below xy plane. So that implies we can stay, as if it's a z-axis, we can go only up, down this much, right? So at most, our angle is going to be pi over 2. And theta, we're allowed to do full rotation for x and y, so 0 to 2 pi. So also going to be our limits for spherical. And then we're ready to rewrite our integrals in terms of spherical. So let me try. Integral 0 to 2 pi, that's theta. Integral 0 to pi over 2, that's phi. Integral 0 to 3, that's rho. Then 9 minus x squared minus y squared, I'm going to rewrite it as 9 minus x squared minus y squared is 9 minus r squared. And you recall that r equals to rho sine phi, so we're going to get 9 minus rho sine phi squared. Distribute square down the road. Don't forget to pay the price. Price is to switch to spherical rho squared sine phi, and then d rho d phi d. That's how spherical integral is going to look like in this case.